Percent distribution. Who is getting the disease? That is what is discussed in percent distribution in descriptive studies. As doctors, this is what we easily understand and this is what is important to us. Percent distribution depends on, as you can see, age. For example, measles, cancer, atherosclerosis. You know that measles is very common in childhood. Atherosclerosis and cancer are increasing in occurrence as age increases. Here, I would like to again tell you one important point, that measles was once a disease we thought that we could eradicate like smallpox. Recently, our dreams have been badly shattered, and that is because measles is showing resurgence in recent years. It is not that the vaccine is failing, but the problem is that people are showing increasing disinterest towards vaccination of measles. There have been a lot of notorious reports in the circulation which have falsely associated measles with a lot of diseases which have caused a lot of furor. Especially in developed countries like the USA and Canada, people are going away from vaccination, and these countries had almost eradicated measles from their geography. Unfortunately, because of the falling rates of vaccinations, measles is showing a comeback in those children. Let me tell you here also that measles is not a disease you would like to kid with. It is a very serious disease. Either it is fatal, if not fatal, it leaves the child severely malnourished and prone to various other infections. Measles also demonstrate a phenomenon which is very peculiar, and that is a phenomenon called as shifting. This is not the shift or the drift of the influenza virus, but this is a demographic shift. What do I mean by demographic shift? It means that measles, which was earlier attacking children mostly under 1 year of age, now does not get children under 1 year of age to attack. Therefore, measles is attacking progressively older children. Now it is very common to see older children, even adolescents, having their first attacks of measles. This is again because of the falling levels of herd immunity, as we saw in the last class. So herd immunity is going down because of routine vaccination rates are going down, and therefore measles get people who are unimmunized and it spreads. The children pool is saturated, so it is spreading to older people. This is another important phenomenon, has not been very recently tested. I could see that this could be tested in a number of ways in coming exams. So something you should know. Coming to the next point in percent distribution is diabetes and obesity. These kinds of diseases are more common in females. I am sure you have a number of other examples also wherein you know which are more common in males and females. So obviously it is important to know that. Here I have one example more in my mind, and that is about AIDS. The very nature of AIDS, that it was very frequently found in homosexual males, gave us the hypothesis that maybe HIV has got something to do with sexual intercourse, because it was predominantly found in homosexual males. So that was a disease which was predominantly found in males, and that was a very important clue towards throwing us on the path of the hypothesis that HIV has got something to do with sexual intercourse. Next is ethnicity. Again, many diseases are particular to particular ethnicities. Marital status. Marital status is said to prolong life. Now some people dispute that. Some people say married people don't live longer, it just seems longer. But apart from this, marriage surely does confer longevity. How does it do that? You can say that it's a sort of bias. People who are well settled in life, people who are more sober in life, tend to get more partners, and therefore they are married. Also, marriage gives a sense of stability and emotional companionship, which helps a person deal with day-to-day problems and decreases chances of diseases like depression. So therefore, marriage is proven to be protective for the duration of life. So that was about married. About the unmarried people, you can see that there is an increased rate of suicide in them, there is an increased rate of depression in them, and there is also an increased rate of various anxiety disorders amongst the unmarried. Occupation, some background information about occupation. This was basically started in UK. So they were amongst the first people who classified the people according to their occupation. Problem with the classification on occupation is that worldwide different scales are followed. So it's like comparing apples with oranges. You know that if I have to compare two things, they better be similar. If I am comparing apples with oranges, the comparison simply does not work. The problem with occupational classifications today is that there is no single classification in the world which is universal. Every country, every region has different classifications. Even in India, for those of you who are interested in especially MCI, the classification of occupation in India also is varied. You have Kuppuswamy scale, then you have modified Kuppuswamy scale, then you have Pratik scale. So there are various scales on which you measure occupation. Then there is Prasad scale also. We'll have a short note on occupation classification so that you are abreast with that also. Social class, we have already seen the rich are by far protected for a lot of diseases and the poor share an inappropriate burden of disease. Behavior, stress and migration are miscellaneous factors. Behavior also we have stressed in detail. We have seen alcohol, we have seen smoking, we have seen that these habits are basically behavioral and therefore they cause disease. So basically behavior in these cases is the primary reason of disease. You would also remember now that we had hence called man today is the agent of his own disease, and that was because of these behavioral factors. Stress. Now you go around anywhere, you see many people talking about stress. Some studies say that stress is unfairly being targeted as the cause of human disease. But on the other hand, there are some diseases which are genuinely associated with stress and they can be aggravated with stress. CHD, rheumatoid arthritis, psoriasis, bronchial asthma, these are some notable examples which are exaggerated by stress. Migration, we saw a lot of rural diseases are becoming urban. That is one problem, which is migration. Especially the mosquito vectors which were rural are now found in urban areas also, because there is a lot of new construction happening in urban areas which leads to a lot of collection of cesspools which are very favorite places of mosquito breeding. Therefore, there is an increased density of mosquito vectors which propitiates malaria spread. The next slide you see is that of something called as a bimodal distribution. When you talk of percent distribution, you'll have a graph of the incidence or the prevalence in a particular age group. Say for example, I want to have a graph of hypothyroidism, okay, and I want a neonatal hypothyroidism. That graph would look very much like this, okay, because I said neonate, I just want the first year of life. What you can see in the slide is something called as a bimodal distribution. Okay, bimodal distribution means this graph has two modes. It has got two peaks. Okay, see the first peak is here and the second peak is here. So as you can see, this data shows two peaks and this is a bimodal distribution. When you have bimodal distribution, that means that there are two sets of data which have got equal value. Say for example, if you take a disease, Hodgkin's lymphoma. Hodgkin's lymphoma shows a bimodal distribution. It peaks once in life and then later on in later life again the incidence of Hodgkin's lymphoma peaks. So these types of data are called bimodal distribution. I should caution you here, bimodal distribution should only be concluded if after cumulative data the data still shows bimodality. What do you mean by this cumulative frequencies? Cumulative frequencies means when you group data. Say for example, to make it very easy for you, I present the data 1, 2, 3, 4 and 4 again. Okay, I also write then 5, 6 and 6. So as you can see, this data has got two modes. You have 2 4s and you have 2 6. But if I had to club this, I say I club 1, 2, 3 in one segment and the other 3 in the other class. So this is first class, this is the second class of this data. Now you see that the bimodality has disappeared. If I had to plot the first thing to show it diagrammatically, I would have 1, 2, 3, 4, 4, 5 and then 6. Look, bimodal. If I club this, I make this a class 1 and this is a second class, I see that the bimodality has disappeared. So, one of the risks of bimodality is that you must ensure that the data which is showing bimodality, the values are not too close. Problems with interpretation of bimodal distribution, as you can see on the slides, are small number of observations are a frequent source of bimodality. So therefore the data set must be large enough to conclude bimodality, and the absence of bimodality does not signify that the data has come from a homogeneous source. Okay, so this is also one of the conclusions that you cannot make. If the data is not bimodal, you cannot say that it has come from a homogeneous source. Coming to the uses of descriptive epidemiology, first of all, it gives us the magnitude of disease load. Very simple, because we do a descriptive epidemiology, primarily we are measuring disease, so we have the disease load. Then you have clues to disease etiology. That means you have an association of the disease with various demographic parameters, and then you can have an association between these two. That is the first step towards the formulation of hypothesis. Descriptive epidemiology is also used in planning, organizing and evaluating preventive and curative services. This is the backbone for evaluation. Say for example, you got an accident rate, you got a maternal mortality rate by a descriptive study, and based upon this data we can then plan and organize services catering to this particular problem. It definitely contributes to research. Now, formulation of hypothesis. If you remember, we started the whole circus for this thing. We started the whole circus for formulation of hypothesis. So let's spend some time on looking at what a hypothesis is, how it should be formulated, and how it should not be formulated. A hypothesis specifies the population to which it is talking about. It also specifies the cause. It specifies the expected outcome, the dose response relationship, as well as the time response relationship. So all these things are specified by the hypothesis. Again, when I am talking about this is a ideal hypothesis. More often than not, in reality, you would almost never find an ideal hypothesis, because such large data is not at anybody's disposal. Okay, it would take a huge magnanimous study, a very long study to make a perfect hypothesis. More often than not, the hypotheses that you and me come across in daily life are very much incomplete. These are the characteristics of an ideal hypothesis. I have some examples of hypothesis for you. Look at the first example. You can see cigarette smoking causes lung cancer. Everybody knows that. Even the layperson knows that cigarette smoking causes lung cancer. There is nothing new. But for an epidemiologist, this is making very much incomplete sense. I want a lot of more data from this incomplete hypothesis. Look at the second hypothesis. The second hypothesis says the smoking of 30 to 40 cigarettes per day. I specified the number of cigarettes. I specified the time duration per day causes lung cancer in 10% of the smokers after 20 years of smoking. Does it sound better? Yes. Why does it sound better? It sounds better because I can test this. I can test this in various aspects. I can test this on time interval. I can test this on number of cigarettes smoked. I can test this on how many years after I am expected to have cancer. So all these parameters are given. This is a better hypothesis as compared to simply saying cigarette smoking causes lung cancer. Okay, so whenever we try to formulate a hypothesis, try to formulate a complete hypothesis. Sometimes what happens is the data is there, we simply ignore it while we are formulating the hypothesis. So make the hypothesis as complete, as detailed as possible. That finishes our descriptive epidemiology. Very basic epidemiological study. You might be wondering, how does the descriptive epidemiology collect data after all? We talked about a lot of descriptive epidemiology, but we never actually told you how the data is collected. Descriptive epidemiology may employ one of the other designs to get data from the community. And now we'll be looking at those designs. The first design which helps descriptive epidemiology to gather data from the community is cross-sectional studies. The very basic study that we do. More often than not, whatever research an undergraduate student has done, say maybe you have done a study in your UG class, you do studies for ICMR, you do studies to help your postgraduate students, you do studies for your professors, those kinds of studies, more often than not you should have done a cross-sectional study. If you have attempted some other kinds of studies also, good, I congratulate you. But most commonly, what we do, the simplest study design that we know is a cross-sectional study. Now let's have a look at the cross-sectional study. A cross-sectional study is an observational design that surveys exposure and disease status at a single point in time, a cross-section of the population. Before we actually go into the details, let us in our own style put this in really layman's terms so you understand what a cross-sectional study is. Basically, a cross-sectional study is like cutting a cake. When you cut a cake, you are just cutting one slice of it. Okay, so cross-sectional study is exactly that. I am taking a cross-section of the society. What it does, it is not a very powerful study. It just helps me to formulate the hypothesis. What will I do? At best, I'll collect morbidity data. All the rates and ratios that we studied in earlier lectures, those could be collected on the basis of a cross-sectional study. So I get morbidity data. I collect demographic variables around that morbidity data and I try to find out associations between that morbidity and those demographic variables. Okay, so that is what basically a cross-sectional study is. It is often used to study conditions that are relatively frequent with long duration of expression. So, for example, non-fatal or chronic conditions. Why so? Take an example, you did a cross-sectional study for a short duration disease, influenza. Lot many people would be missed out because they got influenza, they got cured. A lot many people will be getting influenza after you do the study. So you'll miss a lot of caseload. Okay. So cross-sectional study is ideally suited for chronic diseases. Cross-sectional study measures prevalence and not incidence of the disease. Very correctly said, and it is very easy to understand. How can a cross-sectional study measure incidence? Incidence is for a duration, an incidence of a disease in 1 year. Cross-sectional study, I am cutting through that year. So when I cut through that year, I am in no position to comment about what happened in the whole year. So if I take a photograph, I am in no position to comment about the film. Okay. Example of cross-sectional studies is community surveys. Cross-sectional studies are not suitable for studying rare or highly fatal diseases or a disease with short duration of exposure. For the same reason, you would not find the representative cases because the cases would have already been dead. Coming to the disadvantages of cross-sectional study. Now, why didn't we discuss advantages? Advantages are few and far between, but they are significant. The most notable advantage is it is a cheap study design. Cross-sectional study is the cheapest study design. It is a very easy study design and it throws you towards the hypothesis. So it gives you those first glimpses of what the etiology could be. Okay, so it is a cheap, it is frequently the first study design to be employed and it is very simple to apply. Disadvantages, weakest observational design. Of all the observational designs that we will be seeing later on, this is the weakest. It only measures prevalence and is not capable of measuring incidence. Prevalent cases are the survivors of the disease. Okay, so dead people are not counted. So it can give me a very false impression. Okay, dead people are not counted, only people who survive are counted. It is something like giving a gallantry award to a person who has come back from a war. Okay, the brave were actually killed in the war. If you have to award bravery, it is those who were actually killed in the war who should be awarded, not those who ran away and came back. Okay, so similarly, the cases who survive are the milder cases. Only those will be counted. Actual grave serious cases which represent the actual burden of the disease will not be counted. So cross-sectional study is not a very good design to study that. The temporal sequence of exposure and effect may be difficult or impossible to determine. Actually, it is almost impossible to determine. Again, the egg or the chicken problem. You can never come to a conclusion whether the egg came first or the chicken came first, at least with a cross-sectional study. The problem is I have both simultaneously. If I do a cross-sectional study, the chicken and the egg are simultaneously present in the room. Okay, the later study designs we will see that we can determine if the chicken was there first or the egg was there first. With cross-sectional study, the problem is that when I do it, the chicken and the egg, that means the disease and the cause are already simultaneously present. So I cannot say who gave rise to whom. Okay. To go back to our earlier examples, I cannot say because the cock is making noise, therefore the sun came out, or because the sun came out, the cock is making noise. So that sort of thing. I cannot say with guarantee what is the cause and what is the effect. Usually don't know when the disease occurred because we are not studying it on a length basis. We are taking a cross-sectional. We cannot comment when the disease has begun. Say for example, I said that you use the study design for hypertension. Can I say that hypertension began in this and this time? No. Can I say that there is hypertension in a particular person? Yes, I can say that a particular person is a patient of hypertension, but a cross-sectional design does not allow me to comment upon the duration of hypertension. Rare events are definitely a problem. Never attempt a cross-sectional design when you have a rare event. Okay, what is the guarantee that when you do the cross-section you have that rare event? So it is a bad study design to study rare diseases. And quickly emerging diseases are a problem because you know very little about that disease and the disease shifts very fast.